So today we'll be looking at the characterization and selection of analytical methods. Some of the aspects that we're going to be looking at today are things that we have said before with respect to what we need to consider when we are choosing an analytical method. So quite often I'll be posting, and when I'm posting, most likely I'll be admitting students when I get alerts that they are in the waiting room to join. Now, when we are talking about a valid analytical method, there are some principles that we have to put in mind when we are selecting a reliable analytical method. There are 6 basic principles that have to be put into consideration when we are choosing an analytical method. And those principles are as follows. Number 1, the analytical measurements that we do should be made to satisfy an agreed analytical requirement. That's number 1. And number 2, analytical measurements should be made using methods and equipments that have been tested to ensure that they are fit for the purpose of the measurement. And number 3, analytical measurements that are made in one location should be consistent with those that are done elsewhere. People making analytical measurements should be both qualified and competent to undertake the tasks, the analytical tasks. Number 5, I mean, when making analytical measurements, you should have a well-defined quality control and quality assurance procedures. Towards the end of this lecture, we'll be talking about quality control, what questions to ask yourselves when you are carrying out quality control, and also the quality assurance. The number 6, there should be a regular independent assessment of the technical performance of the laboratory for you to say that you are having a reliable analytical method. Now, when we talk about quality assurance is what we do to get the right answer for the particular purpose. Any analytical process that you carry out should assure you that the quality of the data that you get is reliable. So the answer should have sufficient accuracy and precision to support the subsequent decisions that are going to be made from the data obtained from your analytical procedure or analytical technique. There's no need of spending any extra money to obtain more accurate or more precise answers if it is not necessary. For example, when you just want to get some qualitative information, the answer is yes or no. Then the accuracy or the precision may not be very important. If I ask you, is this solution acidic? The answer is yes or no. As to how much acid is present or how acidic that particular solution is, or how basic that particular solution is, that comes with a different analytical procedure, the quantitative aspect. But if it is qualitative, you just need to say, yes, it is acidic, or no, it is not acidic. Now, when we talk about the quality assurance process, there are specific items that have to be observed. And these specific items will come in form of questions. Number 1, the objectives of your quality assurance process. And the question here is, why do you want the data and the results? and how are you going to use those results. Number two, you need to ask questions about the specifications. How good do the numbers have to be? You write specifications that you are going to gauge for you to say that you have a good quality assurance. One, you need to pick the methods that are going to meet the specifications that you have laid down. You also need to consider the sampling, the precision, the accuracy, selectivity, sensitivity, detection limit, robustness, and rate of false results. We'll be discussing most of these aspects as we go on. You need to employ blanks, calibration checks, quality control samples, control charts to monitor the performance of your analytical procedures. You need to write and follow your standard operating procedures. Remember, we talked about standard operating procedures in the beginning of this unit. Number three, you need to do an assessment. And the assessment that you need to do is to find out whether the specifications that you laid down were met or not. And for you to do this, you need to compare data and results with the specifications that you have laid down. You also need to document procedures and keep records suitable to meet the objectives. And you also need to verify that those objectives that you laid down were met. When it comes to the choice of analytical method, we need to ask ourselves, what is an analytical method? An analytical method is a combination of steps illustrated by the analytical process. And an analytical technique is a chemical or instrumental procedure by which analytical data is eventually obtained. When selecting an analytical method, there are particular things that you need to consider, and the parameters are as follows. Now, the list of these items here, we have actually looked at them before, and in fact, this was one of the questions either in your quiz 1 or in your mid-sem examination. There was a question on these parameters, but remember we had talked about them before. Number one, the sample matrix. The sample that you are going to analyze, is it a pure sample or it is going to be in a matrix mixture of other materials? What is the size of that particular sample? Is it a lot? Is it little? Because now these ones are going to determine the kind of the analytical technique to use. Now, what kind of data is required? Is the data qualitative or is it quantitative? If it is qualitative, for example, in the choice of whether a solution is acidic or basic, just use a litmus paper or an indicator. If it is quantitative, you need to go ahead and do what we call quantitative analysis. For example, you carry out a titration so that you can tell us that this is the concentration of the acid. And from the concentration of the acid, you can calculate the hydrogen ion concentration or the hydroxyl ion concentration. And from that, then you can calculate the pH of that particular solution. Now, that becomes quantitative. But if it is qualitative, it is a yes or no answer. You can simply use a litmus paper or an indicator. What are the expected levels of the analytes? What is the level of precision and accuracy expected in your analytical procedure? Is there a likelihood that there will be some interferences? Again, I asked you to distinguish between an interference and what was the other thing that I asked you? There was interference, and the other one was what? You remember that question?
Contaminant.
Yes?
Contamination. Contamination.
Contamination, yes. Now, when you say that an interference is a substance that interferes, interference is something that interferes. A contaminant is a substance that contaminates. I had a problem with those kind of answers because you are using a word to describe itself. There are very many things that I wrote in that, and you'll be able to see when I give you the papers. Now, number of and frequency of samples for analysis is also a parameter that should be considered when you are selecting an analytical method. Now, a question to consider when you are choosing a chemical analysis method. There are several aspects to look at. For example, the sample-related questions. The question here would be, what type of information is needed about that particular sample? Specifically, you would ask yourself, what types of analytes and samples are examined? What is the range of analyte concentrations or properties of that analyte that we need to measure? If multiple forms of the analyte are present, which of those forms are to be measured? Because a particular analyte may exist in different physical states. Now, which of these physical states do you need to analyze? And then depending on the physical state, then what analytical method are you going to use? What other substances in that particular sample are likely to interfere with the method that you choose? What type of sample preparation do you require? How many samples do you need to analyze? And are there any special safety factors that must be considered for the samples that you have? Then we also look at the method-related questions. At the method-related question, the main question is, what type of information will this method provide? Then you go specifically and ask yourself some sub-questions, and these sub-questions may include, is the method that you have chosen capable of working with the desired samples and analyze? What type of accuracy and precision is required? What is the expected detection range for this particular method? And how selective and robust will that particular method be? Again, as I said, I'll be talking briefly about some of these things I'm talking about. For example, detection range, selection, sensitivity, because these are fingers of merit, which I also mentioned a while ago for you to evaluate your analytical method. How fast will the method analyze the samples? And how many samples can this particular method process at a go? What level of training or expertise is required for this kind of a method? And again, I want to refer to my qualitative and quantitative. If somebody is carrying out a qualitative, the answer is yes or no. And you have to use a litmus paper to tell whether a particular solution is acidic or basic. The level of expertise required for that is very low. You just pick a litmus paper, dip, and then you only make a decision depending on the change of color that that particular litmus paper is going to exhibit. But now when it comes to quantitative, a different level of expertise is required. Okay? Now, what equipment is needed and what costs will be associated with the technique? Will there be any special safety precautions that must be followed for that particular method? Very important aspects that you need to ask yourself before you can choose a chemical method. Then you need to do a method validation. And what is this method validation? Method validation is a process of proving that an analytical method is acceptable for the intended purpose. In pharmaceutical chemistry, the method validation requirements for regulatory submission include studies of performance characteristics. And when we talk about performance characteristics, then that particular method has to have specific figures of merit, which I'm going to take you through. Let me admit some students who are waiting to join. Just a moment. We still have many students who have not joined. About 10 or so students have not joined. Now, the figures of merit. For you to say that your analytical technique is acceptable in the particular analysis, then it must meet these aspects. Number one is accuracy. Remember, we talked about accuracy, that the measurement that you get from that particular method should give you results that are very similar to the true value. Precision, which we also call reproducibility, that when you do several measurements, then the data that you get must be in agreement. Precision and accuracy are different. Precision alone is not sufficient. Accuracy alone is not sufficient, but a combination of the two is very important. Then we talk about specificity. Now, specificity here is that particular method able to discriminate your target analyte from any other analyte that is present in the matrix mixture. Then we also have sensitivity. This is the signal per unit concentration. The linearity, we're going to talk about that. The linear range, we're going to talk about that. We're going to talk about the limit of detection and limit of quantification, which is also in some books called limit of quantitation, and then the robustness of that particular analytical method. So we are going to discuss each of these briefly and see how they apply in analytical procedures. Accuracy, we have talked about it severally. It is how near your value is to the true value. And how do you check the accuracy? You can check the accuracy by analyzing a certified reference material in a matrix that is similar to that of your unknown. A certified reference material will have specifications. For example, if you are analyzing the concentration of copper in a particular sample, you are going to get a particular result. And then you have to get what we call a certified reference material. This certified reference material should have the matrix similar to what you are analyzing, and then it is going to have a specific concentration. Therefore, when you take your certified reference material and you carry out an analysis using your technique, you are supposed to get the same result as that which is specified in the reference material. That way you know that your method is accurate because it is getting results that are very similar to the standard results. Therefore, your method should find the certified value for the analyte in the reference material within the precision, and that means a random uncertainty of your method that you are using. Now, you need to compare also your results from two or more different analytical methods, and they should agree with the expected precision. For example, you have developed a new method, and this new method, you have gotten some data. Now, the question is, If you carry out the same analysis using some standard approved methods, are you going to get the same results? If you get the same results, then we say that you have validated your new method. Another way is to analyze a blank sample that is spiked with a known addition of an analyte. In this particular case, you have a particular sample, and in this particular sample, you add a known concentration of the analyte, and then you go ahead and analyze. What we need to find out is whether you are able to recover, whether you are able to detect that particular concentration you have spiked. If you are able to do that, then we can say that your method is validated. Your method is true. Your method can be accepted. We normally refer to this as a recovery study. If you again go back to the example of analyzing copper, you have come up with a method that you want to detect the concentration of copper in a particular sample, and you carry out your analysis. Then you prepare a known concentration of copper, and then you use your method to analyze that known concentration and find out if you are going to get the concentration that you prepared. If you get the same concentration, then we say that you have a very high percentage recovery. You are able to detect everything that you put in that particular sample. That is a recovery study. You can also use a standard addition method to validate your method or your technique. Any questions so far, students? Do you have any questions? Okay. So we continue. And here, I want to illustrate the spiked recovery method. This is what I was explaining here, analyzing a blank sample that is spiked. And I want to illustrate how you can do that recovery method. And I'm saying, in this recovery method, you have prepared a particular concentration or a sample with a known amount of your analyte. And then you spike it into analysis solution, then find out if you are going to detect that particular amount. That is very important. And how do you calculate the percentage recovery? This is the change in the amount of measured analyte divided by amount of analyte spiked into the sample, and you multiply by 100. And to make sure that this is consistent, you try it with various analyte concentrations. When you try it with various analyte concentrations, then the percentage recovery should be very similar. You are supposed to have a precision. So the spiked studies help us to evaluate the accuracy and the precision of our technique. Now we have a question here to illustrate how you can do that. And the question is, a serum known to have insulin concentration of 11.2 times 10 to the power negative 6 international units per milliliter is spiked by placing 20.0 times 10 to the power negative 6 international units of insulin into a 2 milliliter sample of volume sample. When this spiked sample is analyzed, the measured concentration of insulin is 20.5 times 10 to the power negative 6 international units per milliliter. what is the percentage recovery of insulin in this assay? Very important is to determine the concentration of what you are spiking. And this is how you do it. I just want to explain this. This is what you have put. You have 20.0 times 10 to the power negative 6, and it is in what? It is in 2 mils of the sample. So in terms of the concentration, we can say that what you have is 20 in 2 mils. Let me pick the text so that I can write something better. You have 20.0 in 2 mils. Now, in terms of concentration, this actually translates to 20, not 20, but 10.0 times 10 to power negative 6 times 10 power negative 6. I'm not sure if I'm going to have the negative 6. This is international units per milliliter. We need to agree whether that is true. Because when you have 20 in 2 mils, it translates to 10 per milliliter. So this is the concentration that you have spiked. Now, how did you do this? Before you spiked this, that solution had this concentration. It had this concentration. And after spiking, you did your measurement, and this is what you got. So the question would be, from this analysis, how much did you add? How much you added should be equal to this concentration here, which you got, minus the concentration that was there before the spiking. In other words, when you take 20.5 times 10 to the power minus 6, which is the concentration after spiking, and then you subtract this concentration here, the concentration before spiking, then you are supposed to get the amount that you spiked. When you get the amount that you spiked, then you compare with the true concentration, because you already know how much you spiked. This is how much you spiked. So are you able to detect this? And how do you do that? This is how you go about it. This is just to tell you that when we are using IU, the international unit is a unit of measurement for the effect, not mass of a substance. The variance is based on the biological activity or effect for the purpose of easier comparison across similar forms of substance. When you go to that question, I have already explained that the addition of 2.0 at 20.0 times 10 to the power negative 6 international units of insulin to a 2 milliliter will increase the concentration of insulin by this factor. And it is simply going to be 10 times 10 to the power negative 6 international units per milliliter. Is there any student who may have a question about this explanation, or may want me to clarify further on that statement? Any questions from you before I continue? So we agree that this is the concentration that we have spiked. So we want to find out if we are able to detect this concentration. And how do we do that? We will take the concentration after spiking, and then we subtract the concentration before spiking, so that we get this value here. This is giving us the detectable concentration of our spiked insulin. This is how much we are able to recover. This is how much of the spiked concentration we are able to detect. Now, but we know that 10 times 10 to the power -6 international units per milliliter is the actual amount of insulin that we spiked. When we carry out an analysis, we are only able to detect 9.3 times 10 to the power -6 international units per ml. So the question is, what is the percentage recovered? The method that we have is able to detect what percentage of the spiked insulin. And then we calculate it by taking the signal that we are getting after spiking, divided by the actual concentration that we spiked, and then we multiply by 100. In our case, we are able to detect 93% of the spiked concentration of our sample. So the percentage recovery is actually 93%. So that's good enough analytically. So this result indicates that the method gave a slightly lower value than what is expected. If low recovery is noted for many other samples, then it is a sign that a systematic error may be present in the method. Remember, I told you that any method that you come up with must be accompanied with an error in the measurement. And therefore, in this particular case, we have a -7% recovery. In the definition of your analytical method, you should define whether a -7% is acceptable for the technique that you have defined. If a -7% recovery is acceptable, then we need to accept these results. If it is not, then we need to improve the accuracy of the method that we have. Now, how do we evaluate the precision of a technique? Precision is usually stated in terms of the standard deviation, and it is generally dependent on analyte concentration, and therefore it should be determined at a number of concentrations. It is usually a very good idea to do analysis within a run to see if the precision varies over a range of concentrations. And this can be done by examining a concentration or the signal or response, how it varies with the analyte amounts. Normally, we carry out many measurements, perform 10 measurements, and calculate the standard deviation at 3 concentrations. These concentrations are at low concentrations, at medium concentration, and at high concentrations. Then you can calculate the standard deviation as well as the relative standard deviation at those 3 regions, and you see. Now, what we have here is an illustration of those 3 measurements, and you can, as you can see here, you have a region at low concentrations. Then there's another one here at moderate, and another one here at high concentrations. Then you have the standard deviations calculated at those particular regions. Up here, you do have the relative standard deviation at the corresponding regions, at the low, medium, and high concentrations, so that you can make judgments regarding the precision of your particular method. Now, we talk about specificity. In the messages, repeat. There's something I'm supposed to repeat. What is it? Something I'm supposed to repeat? What I would advise you students that you can unmute yourselves at any point and interject me so that we can clarify any issues that you may have as we proceed. Unfortunately, I have seen this chat a little bit late, so I really don't know what I am supposed to repeat. If you can just unmute. Okay, the spiked recovery method, very good. So let me go back there, students, and explain how we carry out the recovery method. Thank you. So I'm going back to the percentage recovery. And I want to explain what is happening. In this particular case, you are given a sample. And this particular sample has some concentration of insulin. And this is the concentration of insulin that is found in that particular sample. Then you had this concentration here. What you are adding here is 20 times 10 to the power negative 6 international units of insulin in a 2 milliliter volume of that particular sample. Very important is to ensure that you express this concentration as an international unit per milliliter, the way the concentration of insulin in the serum sample is expressed. And that is where I'm saying, if this is 20 in 2 mils, then it translates into 10 per mil. That is 10 times 10 to the power negative 6 international units of insulin per milliliter. So in terms of concentration, what you have spiked is actually 10.0 times 10 to the power negative 6 international units per milliliter. We want to find out whether we are going to detect this concentration when we carry out an analysis. What did this person do? After spiking, he carried out an analysis, and then he found that the concentration of insulin in that spiked serum sample was 20.5 times 10 to the power negative 6. What we are sure of is this, that before we spiked, there was 11.2 times 10 to the power negative 6. After spiking, we have able to detect 20 times 10 to the power negative 6. So the question is, how much of this concentration that we spiked are we able to detect? And for us to do that, we need to take this value here, which is the concentration after spiking, and we subtract this value here, which is the concentration before spiking. That is going to give us the detectable concentration after spiking. And what we are finding is shown here. I want to go to this. So when you take 20.5 times 10 to the power negative 6 international units per milliliter, and I am saying that this is the signal after spiking, and you subtract the concentration before spiking, then you are able to get the concentration. You are able to get the concentration that we are able to detect after spiking, and this is the concentration that we are getting. Now, what we know is that we actually added 10 times 10 to the power negative 6. But we are only able to detect 9.3 times 10 to the power negative 6. So the question is, what is the percentage concentration that we are able to detect? And this is what we are calling the percentage recovery. And therefore, we take what we are able to recover divided by the actual concentration that we spiked, multiplied by 100, and you are getting 93%. Have I clarified your question? The students who wanted us to repeat? Have I clarified?
Yes, it's clear.
Thank you very much. So going forward, I would encourage you to just unmute and ask if you're able to do so, so that I can answer your questions at the point of asking. Okay, so you will allow us continue. We were talking about the precision, and we talked about this. I explained these three regions, and then we had just started specificity. The specificity of a particular technique is also known as selectivity. And this is the ability to discriminate between an analyte and anything else that is present in that particular sample. And the specificity or selectivity of a method is discussed against the possibility of interfering substances that you may have in your analytical solution, or that may be present due to the matrix effects. Now, all likely interferences should be investigated and their effects on analytical response determined over a range of concentrations, so that when you are coming up with a particular method, we know that when you are detecting this particular analyte, you are likely to encounter interferences from substance 1, substance 2, substance 3. Now, how much interference are you likely to get from substance 1? How much interference are you likely to get from substance 2? How much interference are you likely to get from substance 3? And have you done anything to mask the interferences? Have you done anything to ensure that those interfering substances are not detected at the particular parameters that you have determined? So that's why we are saying that measures can be taken to mask, eliminate, or separate any interferences from the analyte. And once you do that, you can carry out further evaluation. Here I have said, check one of the articles that I published in 2010 on masking of interferences. And I explained this one in class a while ago when I talked about the detection of dopamine, ascorbic acid, and uric acid. My target analyte was dopamine, but this dopamine exists alongside uric acid and ascorbic acid, and the concentrations of these other two are extremely high compared to the concentration of dopamine. That was number one. Then number two, I was using an electrochemical method. The electrochemical signal of dopamine, that of ascorbic acid, and that of uric acid are exactly at around the same potential. And therefore, if you just detect, due to the very high concentrations of the uric acid and the ascorbic acid, then you are likely to only detect those two, which are not my target analytes. If they are not my target analytes, then they become my interferences. But I was able to come up with a way of masking, and then you can just check out the arguments of the masking approach in this particular article. Now, the study of interferences can be done by analyzing potential interference. And then you compare their signal with that of the analyte using this particular equation. Here you are carrying out what we call the percentage specificity of your analyte. So the question is, what is the concentration of the interferent or the concentration of the interference substance compared with the concentration of your target analyte? So you have the concentration of your interference divided by the concentration of your analyte multiplied by 100. If the concentration of your interference is very small, then it means that your method is more sensitive to your analyte than your interference. Therefore, the smaller the numerator, the better. And that is where we are saying that if it is less than 6%, then that particular method is said to be specific or selective. We also talk about limits of detection and limits of quantitation. And we can start with the limit of detection. And here our question is how high and how low are the concentrations of analyte can be detected reliably. This detection limit is also sometimes known as the limit of or lower limit of detection. And we define it as the smallest quantity of analyte that is significantly different from the blank. Remember, the blank is the analytical solution that doesn't have any of your target analyte. So here you need to compare the response from your blank to the response of a small amount of your analyte. And I said that you carry out 10 measurements. Then when you carry out 10 measurements, you get the standard deviation of those 10 measurements of the blank. And I want to say this, that the blank has no concentration of your analyte. It has 0 analyte concentration. That does not mean that you're not going to get an analytical signal from the blank. I'm saying so because when you talk about 10 measurements of the blank, and those 10 measurements are giving you a standard deviation, you'd expect those 10 measurements of the blank to have a 0 analytical signal. And if they have a 0 analytical signal, then the standard deviation should be a 0. But in practical sense, it is not likely that you're going to get a 0 signal for blank measurement. You are going to get a signal. So when you carry out 10 blank measurements, the limit of detection is going to be calculated by 3.3 multiplied by the standard deviation of the blank, and you divide by the sensitivity. Sensitivity here is the slope. It's the slope of your analysis. So that's how you do it. You take 3.3 times standard deviation of the blank and you divide by sensitivity. Here we call it calibration sensitivity, but to avoid ambiguity, just say that you divide by the slope. You divide by the slope. Remember this, very important. When you are carrying out an analysis of the blank, then you are doing it at a zero analyte concentration. When you are carrying it out at zero analyte concentration, you remember when you are drawing your calibration curve, this is Y, and in the Y we have the signal, this is X, and this X is the concentration or the amount of analyte that you have. At zero analyte concentration, that corresponds to X is equal to 0, and X is equal to 0 is actually the Y-axis. Now, that Y-axis is going to give you some signals. It's going to give you a signal, a signal, signal. So that is why I am saying that the standard deviation of the blank is also the Y-intercept, because that measurement, you are doing it at zero analyte concentration. The zero analyte concentration is where X is equal to 0, and X is equal to 0 is the Y-axis, and the value that you're going to read is the value at Y-intercept. So when you have Y is equal to mx plus c, this is C is actually the Y-intercept, and this Y-intercept is going to be associated with some standard deviations, plus or minus. This plus or minus is the standard deviation of your Y-intercept, which you can also use instead of the standard deviation. In fact, it is a standard deviation of the blank. Okay, I'm going to illustrate that as we go on in a particular example. Any questions, students? Any questions? Okay. So you will allow us continue. There's something we call the signal to noise ratio. I explained what a noise is in a particular result. When there is so much noise in your data, then you get something like this. Let me show you. You get something of this nature. This particular signal here we say is noisy, because if you look at this, it is not smooth. So when it is not smooth, then we say that the noise is very high. So it is important that you calculate the signal to noise ratio. And the signal to noise ratio is one of the parameters that you report in your analytical measurements. Now, limit of quantitation. Limit of quantitation is the lowest concentration of an analyte that can be determined with an acceptable accuracy and a precision. How do you determine the limit of quantitation or limit of quantification? The method is very similar to that of limit of detection. The only difference is this value here, 10. You use 10 instead of 3.3. For LOD, you use 3.3. For LOQ, you use 10. So 10 multiplied by the standard deviation of the blank divided by the slope. So everything here else remains the same. The only thing that changes here is 10 from 3.3 to 10. And that's basically how we determine the limit of quantitation or limit of quantification. Sensitivity. Sensitivity here is your response signal per unit concentration. That's why we are saying that response changes to concentration changes in the analyte. That gives us the sensitivity. The ability to discriminate between small differences in analyte concentration is very important. We look at the slope and the reproducibility of the calibration curve so that we can infer the sensitivity of our particular method. And that's why we are saying that we evaluate the slope of a calibration curve. If it is very steep, it means that our sensitivity is very high. Okay? And then we can compare this one to the limit of detection. That is the smallest amount, and that is reliably detected. The lower the limit of detection, the higher the sensitivity of our method. Again, I ask any questions? Okay. This is a graph that I am using to describe two things. Calibration sensitivity is just the slope of your calibration curve. We also talk about the analytical sensitivity, which is the slope of your analytical, of your calibration curve divided by the standard deviation. Remember the standard deviation, for example, in this particular case, you have 1, 2, 3, 4, 5 measurements. Normally 5 measurements we say analytically are not enough, but we encourage 6 to 10 measurements so that you can have what we call reliable amount of data for good analytical reporting. And therefore, you get the standard deviation of the measurements. Then from the standard deviation of the measurement, you divide the slope, and you're going to get the analytical sensitivity. So it's very important that you distinguish the calibration sensitivity from the analytical sensitivity and how we obtained these two. Now, we have a question here. A new method for detecting the herbicide atrazine in water results in a linear calibration curve at low to moderate levels of this particular analyte. The baseline fit for the curve was y is equal to 0.207 plus or minus 0.001 x plus 0.008 into brackets plus or minus 0.006, where y is the measured response, x is the concentration of the atrazine, and the values in parentheses, the values in brackets, are the standard deviations of the measurements. Estimate the limit of detection and the limit of quantitation for this assay. Now, limit of detection and the limit of quantitation. Now the question is, what we are supposed to isolate is the important aspects. Because we say that LOD is equal to 3.3 multiplied by standard deviations of the blank. Standard deviation of the blank, and you divide by the slope. So what is the slope here? And what are the standard deviations of the blank? That's what we need to isolate. From this particular equation, this is going to be our slope. And I said that the standard deviation of the blank is that which is associated with the y-intercept. So that is the standard deviation of the blank. I explained when I showed you that a blank measurement is going to be at x is equal to 0, which is the y-axis, and any point there is going to be a signal at 0 analyte concentration, which is actually our y-intercept. Therefore, this is what you are supposed to have, and for LOQ, you are using 10. Therefore, for us to do that, this is a explanation. So LOD is given by 3.3. I have explained where this one is coming from, standard deviation of the blank, and this is what? Our slope. And this is the value you are getting, and then you are giving the answer correct to one significant figure. You can explain why we are giving correct to one significant figure. Remember how we give our answers in multiplications, divisions. Then LOQ, we use 10 multiplied by 0.006, again, the standard deviation of the blank, divided by the slope. I explain this, and that is what you are getting. And this is how you are supposed to express your answer. Any questions, students? Okay. If there are no questions, we continue. The same question is here, but information is here, but the question is different. You are told that a new method for determining the herbicide atrazine in water results in a linear calibration at low to moderate levels of the analyte. The best line of fit for the curve was this. We have seen this equation in the previous, where y is the measured response and x is the concentration of atrazine. And the values in brackets are the standard deviations. What is the calibration sensitivity for a sample containing 20 milligram per liter of atrazine? What is the calibration sensitivity for a sample containing 20 microgram per liter of atrazine? And how will this sensitivity be affected as the concentration of the atrazine is increased? And the calibration curve is given. The calibration curve is given. You see, when you have this question, remember, this is going to be our sensitivity. We need to check from the calibration curve if this value lies within the linear range. If it lies within the linear range, then this is going to be the sensitivity. Okay? So, look here. When we talk about 20 microgram, 20 microgram is given by 20 is here. So you actually go like this, and you realize that that value is within the linear range. If you read very well, find that it is there, and it is within the linear range. If it is within the linear range, then the sensitivity is the slope of this line. And that sensitivity, students, is given in this particular equation. That sensitivity is given here. And therefore, the calibration sensitivity for this concentration is 0.207. In fact, that one is explained here. The concentration of 20 microgram per liter is within the linear range of the assay, and therefore the calibration sensitivity at this point is equal to the slope. Okay? Then when you analyze, the sensitivity will decrease at concentrations above 32 microgram per liter, because from this, from around 32, you realize that we are deviating from the curve. So we are deviating from the curve. The linear extrapolation is deviating from the curve. And therefore we say that the calibration sensitivity is going to decrease. You know, that's where the calibration curve is leaving the linear range. It starts to curve off, right? Therefore, the slope begins to decrease at higher concentrations. I will explain that one further in details, maybe when we meet in class, and I do illustrations in class. Linearity, this measures how well a calibration curve follows a straight line. And it shows that the response is proportional to the quantity of analyte. That proportion, I said something here, that the increase in the concentration may exhibit increase in the analytical signal, or the increase in concentration might inhibit increase in the analytical signal. So whichever the case, we are supposed to have a scenario where there is a proportional relationship between the concentration of your analyte and the signal that you are getting. And that is going to give you a calibration curve. From that calibration curve, you can isolate the linear range. And that linear range is going to give you what you call the calibration sensitivity. So most analytical methods are of a comparative type, and therefore they require calibration against accurately known standards so that you can get quantitative, reliable data. Where possible, the calibration data should show a linear relationship between analyte concentration and a measured signal. However, it is acceptable under some circumstances. So this is a calibration curve where you have a signal on the y-axis and the concentration on the x-axis. And when you get the slope, here you are able to get the sensitivity. I think there was a question in your midterm examination on this kind of a graph. Most of you were able to get the answers correct. Now we talk about the linear range. This is the concentration span over which linearity, accuracy, and precision are acceptable or meet the specifications of a particular analytical method. The linear range is the concentration span over which that particular calibration curve is showing a straight line. Then we have a dynamic linear range, which is the concentration span over which there is a measurable response. And we have a graph that is illustrating that. So here you have a curve, and this curve has this portion here, which is linear. We are calling it a linear range. You will realize that when you superimpose a straight line, that region lies exactly on the straight line. Then we do have a dynamic linear range where we are getting some detectable signals. And at this particular point, we are having the lower limit of detection. And then at the uppermost, we are having what we call the upper limit of detection. So when we further look at the dynamic linear range, it is a linear region of calibration curve where the lower limit is 10 times the standard deviation of the blank. Remember, we talked about the limit of quantification, where we calculate as 10 multiplied by the standard deviation of the blank, and we divide by the slope of that measurement. We have limit of linearity. Limit of linearity is illustrated in this graph. Limit of linearity, that is what, you know, the upper limit of our linear range is the limit of linearity. Okay? Now, robustness. Robustness, what we need to ask ourselves is the method that we have developed. How stable is this method when we make changes to some parameters? That is the robustness. So we are saying that the robustness of analytical method refers to its ability to remain stable when subject to small changes in method parameters, such as, for example, temperature and pH. After all major parameters, we need to alter all major parameters in order to ascertain when the method ceases to function in accordance with the specifications. And therefore, we actually talk about stability studies. Is it stable? If it is stable, it is within what pH range? Against what temperature range is our method stable? And we also carry out time stability. How many days is this method going to remain stable? Then you carry out analysis and you give specifications. Quality control analysis. You need what we call a control material, which should contain the analyte. And this analyte should have a matrix that is very similar to the sample of interest. And it should be stable. And you analyze this one several times so that you can have consistency for your lab and the technique. Then there's what we call a control chart. I'm going to show you a control chart. A chart that shows the results over time when the control material is being analyzed. Then you have error assessment. You need to identify all sorts of errors and how you can correct those errors in your analysis. This is what we call a Jennings control chart. And I'm going to give an illustration of how this chart can be used here. For example, an analysis of cholesterol in a control serum sample gives the following results. You have 187, 198, 191, 189, 194, all this. These data are used to construct a Jennings control chart for this method. Then a new measurement for the same control material gives us a value of 200. Is this value in control or out of control? In other words, is it within the Jennings control chart? When using an allowable range of mean plus or minus 2 standard deviations, is this technique operating at a level that is satisfactory to this sample analysis? Let me explain what you're supposed to do when you get this kind of questions. Number one, arrange this data in some order, increasing or ascending or descending order. And when you actually you realize that this data you have the lowest value is it 186 and the highest is around 200. Then get the mean and the standard deviation. When you get mean and the standard deviation, then you fit the mean and the standard deviation here. You fit the mean and the standard deviation here. And when you do that, then you are going to answer questions, and that is being explained here. For example, based on the 20 values, you realize that the mean is 193. And the standard deviation, is 4. Now, what is defined as an acceptable limit here is mean plus or minus 2 standard deviations. So what is the upper limit and what is the lower limit? You'll realize that the upper limit is 193 plus 2 standard deviations. You know, standard deviation is 4, so it is plus 8. And this gives you what? 201. And what is the lower limit? It is 193 minus 8. And this is going to give you what? 185. So according to that, it means that any values between 185 and 201 are acceptable. What value are we evaluating? 200. Is 200 within this range? Yes, it is within this range. So we say that this 200 is within the acceptable range. And therefore, the results are in control. They are within the Jennings control chart. And therefore, the method can be used for other samples. That's how you evaluate this. Any questions? Okay. If there are no questions, then you allow me. I'm just finishing the next few minutes so that I can take record of attendance and then release you. Sampling errors. You need to avoid sampling errors in your analysis. You use more of the original sample to decrease the sampling errors. And this may be able to avoid non-representative aliquots. And we want a representative sample for that. If the original sample is homogeneous, remember we talked about homogeneous and heterogeneous sample. And it is very easy to sample when to obtain a representative sample when the sample is homogeneous. You just go for the random sampling because every aspect or every space within that particular homogeneous sample is a good representative of the rest. If the sample is heterogeneous, then I explained some statistical methods that we can use to identify a suitable sample for analysis. Sometimes we may carry out pre-treatment of a sample to put the analyte in analytical form and at a particular detectable level. So that's also very important. Then for you to compare types of samples, you select each based on, you select the best sample for each of the analytical protocol. And I've given a table here that can give some guidance. For example, when you have a random sample, a sample selected so that any portion of the overall material has an equal chance of being chosen. Very good for homogeneous samples. Any questions so far, students? Any questions? There's a student who has run out of power, has actually written to me, but the student did not tell me who the name is. Kindly ask the student to send the name so that I can consider that when I'm taking the record of attendance. If there are no questions, students, I will ask you to wait for record of attendance, which I want to take, after which I am going to release you. So just a moment. I've stopped sharing so that I can take record of attendance.